The last topic I want to cover on the video lecture are ions. So ions are really just charged atoms. You can have a positively charged atom, which is formed by when you give up an electron, you're losing that negative charge. And so losing a negative charge means the positive charge will prevail, and so you've got a positively charged ion. The opposite, the negatively charged ions, you've gained an electron, so you've gained negative charge. Now you've got more negative charge than positive charge, so you have a negatively charged ion. These ions have names, these ion types. So a cation is a positively charged ion, positively charged ion, and the opposite, the anion, is a negatively charged ion. We care about ions because ionic bonding is so named because it's bonding between ions. Usually the cation will give an electron to the anion, then you've got a positive charge and a negative charge, and you remember from magnets, positives and negatives are going to attract each other, and so then it's given up the electron, so they've become more stable, and then they stick with each other because now the positive and negative charges are being attracted. But we're going to get into that more later. Today we're just interested in really the sizes of ions. There's an example in the book about how the size of ions impact whether it's zinc and cadmium, whether you are whether like zinc is necessary for biology, but cadmium is poisonous, and that the difference between them, they're in the same. You can see zinc and cadmium, they're in the same group, but cadmium is bigger, and so that it means it has a different biological effect. So the size of ions isn't a trivial point. So we'll look first at cations because it's a little easier to see their size difference. So we're going to look again at sodium, just because sodium, period 3 is a really convenient one to look at, so we will continue to do so. We've got sodium, and that's its nucleus. Then sodium's electron configuration, remember, is 1s2, 2s2, 2p6, 3s1. So we've got 3 energy levels, and we've got on that first energy level 2 electrons. The second energy level, we've got 2 plus 6, so 8 electrons. 1, 2, 3, 4, 5, 6, 7, and 8. And then on the third energy level doesn't cross the second energy level. We've got our last electron, that one. So sodium, we've got the nucleus, and then 1 energy level, 2 energy levels, 3 energy levels. So let's say when it forms the ion, it takes that that electron in the third energy level, and it gets rid of it. So really, the entire third energy level is gone once that electron leaves, and so then you just have the 10 core electrons, the 8 in the second energy level and the 2 in the first. And so you've gotten, because you've taken away this third energy level, you've gotten a smaller atom. You've taken away that outermost shell, and so then you just have these two. So a cation, so we've got we've got Na plus, that's how you designate that it's an ion, given up 1 electron, so it just has a plus 1 charge. You don't have to actually write the 1, but for calcium, so we'll do magnesium because it's the same level. Magnesium, you would write magnesium 2 plus. And for ion charges, you write the number before you write the sign. But yeah, so this sodium ion is smaller than the regular sodium atom, than the neutral sodium atom, because you've given up that outermost energy level. On the reverse side, so looking at anions, we'll look at fluorine over here. So fluorine, where our electron configuration is, so we'll look at fluorine and give it a little nucleus. So we've got 1s2, 2s2, 2p5. So we're going to have 7 electrons in the 7 valence electrons in that second energy level. So our first energy level is going to have our 2 electrons. Then our second energy level is going to have the 7. 1, 2, 3, 4, 5, 6, and 7. So let's say we have another electron coming from somewhere, maybe from that sodium that we just took an electron from, and we add an electron in. And that is going to add a negative, and electrons are trying to stay away from each other. They're repelling each other. So adding that electron means the electrons are going to be a little bit farther apart from each other, and so that added electron repulsion is going to make the ion a little bigger. So this fluorine anion, and you just give it that minus charge, is bigger than the neutral fluorine. And you can look across the periods to see differences in the sizes. One thing to note, as you're going down a group, your ion is always going to be bigger than the period before. So like this potassium ion is going to be bigger than a sodium ion because it's got one more full energy level. And so it's following that same trend as just atom size. As you go down a period, you get bigger ions. The pattern going across the period is a little more complex, but still follows your intuition, remembering the effective nuclear charge. I'm just gonna keep coming back to that concept. It's really important for understanding what atoms are going to be doing, especially for this ionic bonding. So we'll look at the figure in your book that's looking at ions as you go across periods. One important thing, so ions are really, we'll get into it more as we fully go into bonding, but atoms are trying to get into a stable, it's called a noble gas configuration. Because the noble gases are so stable, that's really the energy state that all the atoms want to get to one of these, and they really just want to go for whichever one they're closer to. So like fluorine, because it's just one electron away from the neon, it's going to try and get that one more electron to get to neon, so it's going to pick up an electron. Sodium is also one electron away from neon, but it's one electron more than neon, so it's going to give up that electron to get down to there. So really the way of remembering what an ion is going to be, you can look at the group number and you see, the group number works for the cations, not for the anions. You're looking to see how far away the atom is from the noble gas, and whichever way it's easier for the atom to get to, so like the group 1 and 2, it's easier to go, like magnesium, it's easier to lose 2 electrons, and then it's in its configuration, instead of gaining 6 more. So that's why magnesium forms a positive cation. On this side, oxygen, it's easier for it to gain 2 electrons instead of losing 4 more. 1, 2, 3, 4, 5. Instead of it losing 5 electrons. So we'll get more into that later, but that's just a quick primer on why the ions are what they are. So this figure in your book is looking at the sizes of ions going across the period and down the group. So like I mentioned, going down the group, you've got the ones in black are the atoms, like the neutral atoms. The ones in red are anion values. The ones in blue are cation values. Sorry, I had that reversed. The ones in red are cation values. The ones in blue are anion values. So you can see, just like the atoms get bigger going down a period, that's lithium, sodium, potassium, rubidium, the cations are also increasing in size going down the group. And the same trend on the anions. So going from oxygen to sulfur to selenium to what is it? Tellurium. You're increasing in size in the neutral atom and in the ion. So that's what we were expecting. We're also, so before we look closely at them, with effective nuclear charge, looking at the cations, so they're giving up electrons. Would you expect them to be smaller? So would you expect like the cations in group 3 to be smaller or bigger than the cations in group 1? They're giving up more electrons. So because the cations in group 3 have that effective nuclear charge of 3, as opposed to an effective nuclear charge of 1, well, those are the effective nuclear charges in neutral atoms. We're really giving up, lithium gives up the 1, beryllium gives up the 2, boron gives up the 3. So those are electrons that are being given up. So really, those effective nuclear charges aren't applicable anymore because we've given up all of the valence electrons. So let's go on the actual periodic table. So you can see lithium has 3 protons, beryllium has 4, boron has 5, and they've given up their electrons, but they still have the same number of protons, and they also, because this has given up 3, this has given up 2, and this has given up 1, they all have that helium electron configuration, because they're period 2, so they go to the noble gas before them. So each of these, once you've given up 1 electron, you have 2 electrons left. 2 electrons, 4 minus 2 is 2 electrons left. 5 minus 3 is still 2 electrons left. So they have the same number of electrons, but are increasing their but they have more protons, so those protons are exhibiting a greater nuclear charge. So this effective nuclear charge, they all have the 2 electrons, but this one, each of those 2 electrons is feeling an effective nuclear charge of 3, of 4, and of 5, respectively. And so that's why the boron is smaller, because each of those electrons is feeling a much larger pull from the nucleus, because there are more protons but the same number of electrons. That brings us to our next vocabulary word. We've got isoelectronic. And so iso is a prefix meaning the same. So if you've done anything with atmosphere and weather, an isobar is like the same atmospheric pressure. Isotonic in biology is the same concentration on both sides of a membrane. So isoelectronic is just the same number of electrons. And so like that lithium, beryllium, boron example, those 3 are isoelectronic because they each only have 2 electrons, the 3 ions, the lithium plus 1 plus, the beryllium 2 plus, and the boron 3 plus. All of them only have 2 electrons, and so they're isoelectronic. They all have the 2 electrons. So that's for the cations. Then on the anions, we're looking at oxygen and fluorine. So you've added 2 electrons to the oxygen and 1 electron to the fluorine, because oxygen takes 2 electrons to be the noble gas configuration. Fluorine just takes the 1. And it again is related to that effective nuclear charge. So you remember that valence electrons, like they repel each other a little bit, but the effective nuclear charge has a greater effect than the added repulsion from valence electrons. So this oxygen has its 2 more electrons, but still just has the 8 protons, whereas fluorine is just adding 1 electron and has 9 protons. So each of those electrons is feeling that same effective nuclear charge. So the oxygen and fluorine, they both have the same screening level, so both of them are they're in the second period, so they're really they have 2 core electrons, and then the rest are valence. So they're ignoring the core. Well, the core electrons are doing their shielding, so we'll take away 2 from whatever their charge is. So 8 minus 2 is 6. 9 minus 2 is 7. So the fluorine electrons are experiencing a greater effective nuclear charge, and even when you add in those other that other electron, they're still it's a valence electron, so it's not really interfering with anything. So it's still a greater effective nuclear charge. And so your ion for fluorine is smaller than the ion for oxygen, 2 minus. And that's, again, an isoelectronic pair, because the oxygen, when it adds 2 electrons, has 10 electrons. Fluorine, when it adds the 1 electron, also has 10 electrons. So we've seen how cations work within cations and anions work within anions. But you can also look between cations and anions. So looking at that, at a similar series, so we'll look at sodium, magnesium, aluminum, and oxygen and fluorine. So our 3 cations are the sodium, magnesium, and aluminum. Our 2 anions are the oxygen and fluorine. So aluminum is going to give up 3 electrons, so it's going to go down 1, 2, 3 to get to that neon electron configuration. Magnesium is going to give up 2. It's going to go 1, 2 to get to neon. Sodium is going to give up 1 to get to neon. Fluorine is going to gain 1, and oxygen is also going to gain, or oxygen is going to gain 2. So we've got our 2 anions and our 3 cations. So looking here, we can see that the increase, so this oxygen, fluorine, sodium, magnesium, so oxygen 2 minus, fluorine minus, sodium minus, magnesium 2 plus, sodium plus, magnesium 2 plus, and aluminum 3 plus. That's an isoelectronic series. All 5 of those have 10 electrons, because they all have that neon electron configuration. So we're looking first at the nuclear charge. So oxygen has 8 protons, fluorine has 9, sodium has 11, magnesium has 12, and aluminum has 13. So the charge of the nucleus increases with each proton you add, so the nuclear charge is getting bigger as you go across, or as you look at this isoelectronic series. The ionic radius, so although sodium, magnesium, and aluminum, the atoms, the neutral atoms, are larger than oxygen and fluorine because their sodium, magnesium, and aluminum are in period 3, whereas oxygen and fluorine are only in period 2. In the ion, aluminum, magnesium, and sodium have given up their 3rd energy level so that they can get in that stable 2nd energy level configuration of neon. So they all have the 2 energy levels. So aluminum is having the greatest effective nuclear charge because it's pulling with plus 13, and they all have the same level of screening because they all only have these two core electrons as shielding. All of these ones aren't really interfering with each other. They're, for all intents and purposes, are valence electrons now. So you're increasing your nuclear charge as you go across, which means your ionic radius is decreasing. So looking at an isoelectronic series, your anions are going to be bigger than your cations. So your anions with the same number of electrons as the cations are going to be larger. Your anions are bigger, and as your biggest anion is going to be the one with the largest charge. And then as you go across, the most positive cation is going to be the smallest, because of that effective nuclear charge. And because they're isoelectronic, they're all in the same energy level. They all have the same number of electrons. And yeah, so that is ionic size, and that with all that, we have enough information to start looking at some of the properties of metals, nonmetals, and metalloids, which we'll be doing in class on Thursday.